Okay, we are going to be talking about some heat things today. Excellent, everybody's here. And we're actually going to start the lecture with Tyler doing a couple demonstrations. He'll need half of the class for, well, not one of these two. But before he gets started, let me point out something. You see this stuff here on the screen? Where's that coming from? And it's Rachel already identified where it's coming from, so I'm not going to have her answer. Where is it coming from? Okay, that's from light going through the hotter air. We'll learn soon that light travels with different speeds through different materials. And light goes faster through hot air than it does through cold air. The moisture is going to make a difference as well. So with the two things combined, I can't tell you for sure what it is. But because you have different speeds for the light going through these materials, the light bends. And so what you're seeing there is the result of the light bending as it goes from colder air to hotter air back to colder air. So I just like that we can see that on the screen. Now we're going to start with Tyler doing a demonstration here. This way. So Tyler, go ahead and do your demonstration. And no, it is this way. It's upside down no matter how I do it. Excellent. Okay. I have the scroll lock on just in case you're curious. Well, everybody watch Tyler in upside down motion.
So these two go through each other normally just fine. But then when you heat this one up, it'll expand, hopefully, and won't be able to go through this. That could take a little while.
If you look at the projection of the picture, you see he's upside right on the projection.
That's weird.
This, I guess, is a problem with having the scroll lock set to upside down.
Okay. So let's see here. No, it still goes through. I'm upside down.
Yes, you're upside down, but you know what? The tricky student will understand what you're doing. And they'll say, I can't believe the teacher has the video upside down. And they'll be fine with you.
Okay, yeah. So now it kind of gets stuck on its way through because it's so expanded. But if you heat this one as well, then it's able to go through again because they're both expanded now, which is kind of cool.
Now, one of the keys to note is the hole expanded as well as the solid thing.
Oh.
It got tired of taking video, but that's okay. Now he's going to do a second demonstration that is related to the first one.
Okay, so this has two different types of metal in it on each side, and one of them expands more rapidly than the other. So when you put it in here, it curls because one of them wants to expand really fast.
Rotate so they can see the curl. I got to come over here so we can see the curl. Now, which side is on the outside?
The more expansive one, because heat doesn't make things contract. It makes the outside want to expand and curls it that way.
Now, one thing about that is that both sides expanded. It's just one side expanded more than the other. And so when you make a circle, the outside of the circle, so let's just make two circles, one on the inside and one on the outside. The one on the outside has a slightly bigger radius. And because it has a slightly bigger radius and circumference is equal to 2 pi times the radius, then the one on the outside is slightly longer. And so that's why the one that expanded more went from straight to being a circle with the one that expanded more on the outside, so it was slightly longer. The two are bonded together. So that's the first of Tyler's mini demonstrations. But let's have a clicker question now. What is the equation of state for an ideal gas? As soon as you answer, you might come back up here, Tyler, because you see on the bottom of the screen. Tyler, demonstration. Do you not have yours, Colby, or are you getting the channeling? Okay. So, go ahead and do, oh, yeah, actually, do this one.
I'll do this one. Okay. Well, hopefully this works.
Okay, everybody has answered.
I don't think it's boiling.
Yeah, hold it over that now to finish it off. Okay, so the answers we had were 1, 3, 3, 2. So let's go through these. The first one, heat never flows from hot to cold. Is that true?
No.
Yeah, it's false. Heat always flows from hot to cold. It doesn't flow from cold to hot. Oh, wait. Yeah, it does say, in my brain I said heat flows, yeah. So yes, it is true. I'm sorry, I read it backward in my head. But that is a statement of the second law of thermodynamics, not the equation of state for the ideal gas. The second equation, work is equal to pressure times change in volume. Is that true? Yep. But that's just the definition. That's boiling. Of thermodynamic work. And that one there was wrong. Leaving this here, that's the equation of state. The equation of state relates the state variables, pressure, volume, and the number of molecules and temperature. So now if we look at this, what he's doing right now, he has boiling water in there, high temperature. And then he's going to put it over here, so it goes from boiling water to cool water. What's going to happen when that occurs? Okay, let's see. It was a delayed response. I was like, not again. It must just be Tyler. No, it worked. We kept this one here to show that it really does work, just in case it failed. And Rachel was here to verify, so it wasn't just, you wouldn't say, oh, it's just those two conniving rats trying to, Is your last one going to be ready? Okay. Okay, so, oh, that's right, yeah. So you can go ahead and sit down. So what we saw there was when temperature dropped, the pressure and volume inside, the product of the two, had to drop. So if the volume stays the same, as if the can doesn't crush, what's going to happen to the pressure inside the can? Decrease. So you have a higher pressure outside, a smaller pressure inside. Pressure relates to force. Pressure is force divided by area. So that means the force that's pushing in on the outside, force will be pressure times area, is bigger than the force pushing out from the inside because you have lower pressure inside. So you have more force pushing in than you have pushing out. Well, what happens if you have more force pushing in than pushing out? You have a net force pushing in and it crushes. Now when it crushes, then the volume drops. You had to have that left side, the pressure times volume, drop. So first volume dropped, that made it first the pressure dropped, that made so atmosphere crushed it, and that made the volume drop so that you could reach the equilibrium there between pressure, volume, and temperature. Now I have to point out something else. This is the ideal gas law. Ideal gas. Did we truly have an ideal gas here? No. Thank you, Denford. Why was it not an ideal gas, which is a harder question? What? Okay, we were close to the boiling temperature since we had boiling water, right? So it was just basically boiling temperature. The atoms are definitely going to or molecules definitely going to interact. It needs to be well above the boiling temperature to behave like an ideal gas. But this behavior is still approximately true. It's just not exactly true. It's still going to have, if you lower the temperature, the pressure times volume has to lower. Now, when you change phase, you have a very dramatic change in the volume. When you toss water on a fire, that water quickly vaporizes and expands tremendously. I think the number is like 1,500 times or something like that. They taught us in Fire Academy what it was, but it's been a while since I took Fire Academy. So that water expands a lot. One of the things you may have noted when Tyler was playing with the first demonstration, after they were hot, he put them in the water. And when he put them in the water, you heard a noise. What did you hear?
Was it the water boiling right next to the can?
Exactly. When he put that in, it was so hot, much higher than the boiling temperature of water, that the water that was touching the rods pretty instantly boiled. Not exactly instantly, but very quickly boiled. And so it formed a layer of steam around it because you had that rapid boiling. For that reason, if you have a confined space and you put water on a fire, you're going to fill that space up with hot steam, and if you're not wearing your turnout gear, you'll scald yourself. Okay, we can see right now, what direction is the hot air moving here? Up. Question, what makes a hot air balloon rise? Why does a hot air balloon float?
Because hot air expands.
Okay, hot air expands, and when it expands, that means that the density is less. You have the same mass but a bigger volume. But then we learned about floating. How did density relate to floating? The less dense things will float on the more dense things. So that means hot air will float on cold air. And so to make a hot air balloon, you heat up the air. It's still air. There's nothing special about it. But it's hot. Because it's hot, it's expanded. Because it's expanded, it's less dense. And so you have a buoyancy. And so then that buoyancy is enough to lift up your balloon and some payload as well, which would be, people out having fun. So it's the hot air expanding and thus being less dense, making the hot air balloon float because it's less dense. Okay, second clicker question. Which method of heating is responsible for cooking food in a microwave oven? Oh, that's because, That's not a good sign overall. But it is not the clicker question I was reading anyway. It's supposed to be, well, let me fix this problem. We'll go, go there. Disconnect and reconnect. Everything's out of the water. Work sesame. There we go. Now I should be able to reconnect. Come on, baby. Come on, baby. And voila. Sorry about that delay. Okay, there are three mechanisms for heat. I was thinking that clicker question was way out of place, but the slides looked alike. There are three mechanisms for heating. We've only talked about really one. That is direct contact. If I come and I touch something, I can have heat flow. And we've learned which direction does heat flow from what to what? From hot to cold. So that is conduction, direct contact. Then we also have convection. Convection is easily illustrated. I'm going to have Tyler come up in a minute to do a conduction demonstration. The convection I can illustrate real quickly. I put my hand over here. It gets hot. Why is it getting hot? Okay, now, we always say heat's rising, but quite technically, it's hot air that's rising. But that hot air is taking with it heat. And so the heat rising name is what convection is. The heat is being transported by an intermediary, in this case, the fire, or the hot air. So I have the fire making something hot. Hot air comes up and transports the heat. And of course, this is basically how our weather systems work. Right? You have hot air that comes and heats up the ground, and the ground heats up hot air, and the hot air goes over there. You can make a convection oven where you heat up air, you blow that hot air on the food to cook the food. So, convection. And finally, radiation. The lights are making radiation. Radiation is electromagnetic waves carrying the heat. So let's look at our first one, conduction. Conduction requires contact or physical object. So in this case, we have two things at two different temperatures. Temperature 1 is hotter than temperature 2, so heat naturally flows from object 1 to object 2. The rate of flow of heat depends on a number of things. Number 1, it depends on the size of the conductor. If the conductor has a really big area, it's like having a really big pipe. You can put more through it at the same amount of time. So it flows faster if you have a big area. It also has to do with length. If it's a long conductor, if it's a long distance between object 1 to object 2, it's going to make it flow faster or slower? Slow, right. The longer it is, the slower the heat flows. But then there's a third thing, what the object is. If the object is made of wood, heat does not flow quickly through wood. I think I mentioned a while ago, like before break, walking on a dock, your feet on the wood is not a problem, even though that wood's very hot. Because you put your foot on the wood, and very quickly, just the top skin of that wood transfers heat into your foot, becomes the same temperature as your foot, and then it takes a long time for heat from below to come up through the wood. And so the heat is just for an instant and then stops. That also explains why you can do things like walk on coals. Now, walking on coals is not perfectly safe. I am the poster boy for this. When I was 13 months old, we were living in Sierra Leone. We had wood-burning stoves in the cafeteria. And after baking day, they shoveled the coals out. So one day, my dad went to work, and he was just going to shop, he was principal of school. And I snuck out of the house at 13 months and followed my dad, and I walked through this pile of coals. My dad was lighting up the torch. He thought he heard something, looked out the window, and saw me standing and crying, because let's face it, I was trying to eat, in the middle of these coals. So my dad came out to try to rescue. But it was burning my feet. So I started trawling. And so I still have like scars on my wrist, not a suicide attempt. It was from crawling in the coals. And so it was still melting my skin, so I sat down. And my diaper saved my butt. My dad came pick me up, and the flesh was actually dripping off my feet. Okay, so walking on coals is not perfectly safe. But because the coals are a poor conductor, it's much safer than, let's say, walking on hot metal. Because the hot metal, you put your foot on there, and it'll just keep conducting, and burn you much worse. So I don't recommend, in physics class we always talk about things like, and then there's, a little vapor on your foot if your feet are moist, like often they'll have you walk through some grass before you do fire walking. That gives you a little moisture that will, in a smaller way, do what happened when you put the hot metal into the water, create a vapor barrier. It's still not wise. When I was in graduate school, one of my fellow graduate students was explaining fire walking and how it works. And his students went to the beach that night and were all, hey, let's do it! And so they come back and told, hey, we did it, you were right. And he was like, oh my goodness. Because there's plenty of ways that you can harm yourself trying to walk on fire. And they were college students, public university, barbecue, beer. Then you walk on it. You might not be aware that you're burning yourself and get a coal stuck between your feet. And Anyway, so don't do it. Everyone understand that? Okay. we're going to have Tyler come up and do a demonstration. And for this, we need half the class to come help him. Either side. Excellent. All right.
Should we have one more?
I'll be the last one.
Okay, so these are different metals, each prong, I guess. And so they're going to conduct heat differently. So when it's in the fire, everybody grab one. And when it gets uncomfortably hot, you can let go.
Do not burn yourself, okay? Test to see who's the real man and who's the...
Well, thanks.
Yeah. Yeah, I guess Rachel just let go now. I feel fine.
That's because you.
What? Me cheat? Okay, so we had the first person had to let go. And mine's getting warm, so I'm letting go too. Let's go ahead and stop. We'll be here all day with two of these guys. The third one we'll have to give up eventually, but it'll take forever for the last two. Yeah. So what we saw here was some of us got hot and had to let go. Anyone who just noticed, Tyler's cooling down and getting boiling off of some of these. Nothing off of that one.
That was yours.
No, you flipped it over.
Oh, yeah.
That one was, yeah. So I think it was Denford was on the end. He would have been here all day. What was the difference, Tyler?
The different metals.
Different metals conduct at different rates, different qualities. So what's a good conductor? In general, metals are good conductors. But not all metals are the same. Copper's a really good conductor. So for something like conduction of heat away from the CPU of your computer's central processing unit makes enormous amounts of heat. That's really what limits how fast your processor can work, is how quickly you can get that heat out of there. And so they want to have copper connections if they can to get the best conduction of that heat away. Now, after it goes through the copper conductor, how many people have looked at the cooler on a CPU? Obviously, Colby. Okay, a couple. After it goes through that conductor, what's the next thing that that conductor attaches to? Okay, it's an aluminum block, but what's special about that block? It's not just a brick. Okay, it has a whole bunch of veins sticking up with gaps in between them. And that is to deal with these mechanisms of heating. You have that copper contact between the CPU and the heat sink, as we call it, so that you'll conduct very rapidly from the CPU into the heat sink. And then the heat sink has a whole bunch of little, it's made out of aluminum because it's lightweight and it's a pretty good conductor, has all of these veins that have a lot of surface area. Why the surface area? What's going to touch those veins? Air. Air comes and touches it, what happens to the air? It's warm. When it's warm, it expands and then it goes up. And so heat is removed. What do we call that mechanism? Convection. So it's then passing the heat into the air via convection, and then you have fans to pull that air away so it doesn't come back. And that's how you're cooling. So you're using both convection and conduction for cooling that CPU. So, yeah, not worried about that. Air is a very good insulator, by the way. Air has a very low conduction. So if it's cold out, you might wear something like long johns. What's the purpose of the long johns? To trap air bubbles. Trap the air bubbles so they can't flow and give you a convective cooling. Air, because air is very poor at conducting. Right? A windbreaker keeps the air from blowing away. It's kind of doing that. The long johns are just trapping it. So we have the question that I gave you at the very end of Wednesday. about why we use the spun fiberglass for insulation. We use that spun fiberglass because it traps air. And that air is our insulator. The fiberglass isn't the insulator. It's holding the air in place, and the air is the insulator. Okay, now to convection. Here we see, on the screen, you see an example of convection currents. Here we see a guy sitting in his chair, heating his room via convection. He has a heater over by the wall. That heater heats up any air that comes in contact with it, just like the heat sink on the CPU of a computer. The hot air naturally rises, floats across the top of the ceiling. It's going to cool down some. And as it cools down, it becomes more dense again, sinks back down. This happens on a much bigger scale with our weather patterns. So where is it hottest typically on Earth? The equator. So typically the equator's hot, the air gets heated. As it gets heated, it expands. Because it expanded, it rises. Now as it rises, it actually starts cooling. And because it's cooling, it can't hold moisture. Right? I said that hot air can hold a lot more moisture than cold air. So you have that hot air, usually moist because you're usually pretty close to the ocean in these situations. Hot, moist air rises, it expands and cools, it drops the moisture out. So you get a lot of rain. That air keeps going up. Now it's a dry air. And of course, if it's at the equator, it's got to go either north or south. So that air goes north or south, but it's cooled off, it compresses, and it drops back down. So now you have this dry air that's now cold and dropping down. But as it drops down, the pressure increases. What's going to happen to the density if you increase the pressure? Increase the pressure. It's going to condense it back down, and as it condenses, it makes it hotter again. So now you have a hot, dry air coming down. Somewhere around 30 degrees north or south is typically where it comes down. Well, if you have hot, dry air, you're not going to get any rain, right? What do you get in a situation where you have hot, dry air, no rain? Deserts. So your deserts tend to be here around 30 degrees north or south because of convection. And you have all of that rain in the tropics because of convection. That hot, moist air going up, expanding, cooling, and dropping its water out. So, these things that we learn about, obviously very applicable to global climates and local weather. Finally, radiation. Radiation is electromagnetic waves. Things that are black will radiate incredibly well. Things that are silver will radiate very poorly. So my Oakland Raiders are pretty much covering the gamut. When they wear their dark jerseys, they'll absorb and emit radiation very efficiently. When they're wearing their white jerseys, they will absorb and emit radiation very poorly. Now, this leads to interesting situations for the football team. If they're going to go play somewhere that's hot, what would they rather wear? Black or white? They'd rather wear white because the sunlight has a lot of radiation that comes to us. And the white will not absorb that very efficiently. And so they'll stay cooler. Now you might say, but black, they'll emit radiation a lot better. The radiation efficiency is proportional to temperature raised to the fourth power. Our body temperatures are around 300 kelvins. Compare that to the sun. Temperature is around 6,000 kelvins. Right there. We don't radiate very much compared to the sun. And even though we're far ways away from the sun, the amount of radiation we're going to lose is very small compared to the amount we're going to absorb from the sun. And so if it's cool, you want to wear your white jerseys. If it's hot, you want to, or excuse me, I said backward. If it's hot, you want to wear your white jerseys. If it's cool, you want to wear black jerseys. Now that leads to some chicanery. About 6 years or so ago, the cheating team from the red state went to Southern California on a hot summer day to play football. And back then they had the cheating coach, Mike Shanahan, and he just conveniently forgot that San Diego, the home team, always gets to choose what color they're going to wear. And San Diego had chosen we're going to wear our light jerseys because it's going to be sunny. And so Denver has to wear their dark jerseys. But Shanahan conveniently forgot to bring the dark jerseys. He only brought the light jerseys. So he's like, well, what are we going to do? We don't have another jersey, but they're at home. They've got all kinds of jerseys. And the NFL actually made San Diego play at the disadvantage of wearing the wrong color jerseys. Now, these days, when they're doing crazy things like everybody's wearing dark jerseys for the, Thursday night games?
Color rush, yeah.
Yeah, color rush. I guess they would let it just go. But Denver got an unfair advantage there because, well, Shan's a dishonest man. A dishonest man who completely ruined the career of RG3, I believe. And it has nothing to do with Denver. Nothing to do with any coach for the Raiders either. So, radiation's an important thing in our heating. So here's a picture of a thermos. Here's what the inside of a thermos looks like. Now, if you look at this, one of the first things you notice is the color. What color is it? Silver. Why? It's very bad at absorbing or emitting radiation. Next thing, I come up here to Colby because I'm going to do everything today. Go ahead and just tap it a little bit. Hollow, right? It has a thick wall, it looks like, but it's not thick. It's made out of glass. You can see here at the end where it's not silver, but it's glass. And it's double walled. It has two thin walls of glass. Glass is a poor conductor, so that's why they use glass. What's a poorer conductor than glass? Air is poor. And even worse than air, vacuum. If you have nothing in there, that's going to be the worst. There's nothing to conduct. There's no contact whatsoever. And so inside of this, it's evacuated. You see there it says vacuum, so that you have no conduction. Any heat that's going to conduct from here to the inside is going to have to go all the way along the side through the thin wall. So it has a small area and a large length, minimizing the rate of conduction through a bad conductor to begin with. So you have the silver to stop radiation. You have the vacuum to stop conduction as well as convection, because convection needed some intermediary. There's no intermediary. Can't speak English. There is no intermediary if it's a vacuum. So this is stopping all three mechanisms of heating. Hence, you put something in here and you put a lid on that's going to also stop, so you try to put a lid on that covers the same concepts. And it will keep hot things hot and cold things cold. Right? It's not can only keep hot things hot. It's not can only keep cold things cold. It does both. Now there is the blonde joke about the blonde who put her ice cream and her hot soup in the thermos together because it keeps hot things hot and cold things cold. Well, that's not going to work out. Why? Okay. What it's actually doing is not allowing heat in or out, but if you have the ice cream that's cold and the hot soup together, well, those will be in contact and will exchange heat. So that's why it's a blonde joke. And of course, brunette joke, gray hair joke, I don't care. Right? Some people take offense to those things. Now, the question that I tried to read a while back, which method of heating is responsible for cooking food in a microwave oven? All right. We had 9 people who said radiation, and they are correct. Now, when I say radiation, I mean, what does radiation mean? Okay, it's electromagnetic waves. So a microwave is using electromagnetic waves. Is a microwave safe?
You were microwave.
If I was microwave, you're correct. If you were to put a human in a microwave, or like the joke goes, the old lady putting her poodle in the microwave to dry his hair. Yeah. That's not good. Not good. How does a microwave work? You are using microwaves, waves of radiation, that cause water molecules to rotate. And when they rotate, well, that's making them have kinetic energy. That's increasing their internal energy. You increase the internal energy, you're increasing the average kinetic energy per molecule, i.e. the temperature. And so it's transferring energy directly to the water molecules, and then it's cooking from the inside out. Now, yes, I brought my cell phone with me today. How does my cell phone communicate with the world?
Waves.
Microwaves, to be exact. And so there's some people that are worried that when I go like this, I might be cooking my brain, because this is putting out reasonably strong microwaves. Well, there's been a lot of research because it really is a concern. The microwaves are well below ionizing radiation, which is the level of where you would cause injury for sure. And so all you're worried about is the cooking. There is research that indicates that the blood flow differs. They had people walk around all day with a cell phone taped to their head. Probably not taped, but attached, like with the head piece. And some of them, the cell phone was turned on. They're not making phone calls, but it's turned on, so it's communicating with the towers. And some of it was turned off. It was just doing nothing. And the blood flow was greater for the people that had the cell phones on than the people that didn't, by a small amount. So there is a physiological effect going on. Is it enough to cause damage? The blood flow difference was much less than the blood flow difference from you sitting down to you deciding to stand up. Right? So it's not like it was making a huge difference. It was making a measurable difference. So, maybe there is reason to be concerned. A lot of people consider, we're still doing the experiments to see if cell phones are safe. Give us another 20 years or so and we'll know by looking at, if we all start getting cancers and stuff. So not so sure. Most people think it's probably safe. And it's certainly convenient. Of course, my wife thinks horrible things. I keep it right here in my breast pocket. I'm going to give myself breast cancer, right? You've seen those pictures where they take a picture of a lotus flower. It's got those big holes in it. And then they superimpose on a person's flesh and they say that it's worms or radiation. Yeah, that scares some people. One last thing on microwaves to scare people. I actually have a family member who threw out the microwave in the house because, it modifies the food and kills it and makes it unsafe. No, it's just cooking the food the same way it cooks food when you put it in the oven, except for it's cooking from the inside out. But you're still heating it up just the same. So it's not going to modify the food, not going to make it any less safe than if you cook it. Now, if you're worried about raw food versus cooking food, sure. But if you're cooking food anyway, not a concern. Okay, now we can answer this question. Since everybody answered the last one correctly, I'm pretty sure everyone was paying attention and will answer this one correctly as well. Warehouse is insulated with spun fiberglass rather than just empty space. Okay, this was not as unanimous as I thought it would be. If it was empty space, there would obviously be no convection. And there would be no conduction. So you would remove both conduction and convection if you had empty space. But as soon as you put air in there, which is what you actually have, you would have very poor conduction through air, but pretty efficient convection with air. Because the air is free to move around. You heat it up and it moves. So you have that spun fiberglass to keep the air in place, to trap it, so that you're cutting down on the convection. Right, empty space here, in your attic or in your wall, empty space is not going to be a vacuum, it's going to be air. And so that's why it's not the other answers. Okay, I think we're ready to go to, got to talk about politically motivated topics. The greenhouse effect. First of all, the greenhouse effect is very real. The greenhouse effect has to do with radiation. the Earth has an atmosphere, and that atmosphere is transparent to visible light as well as radio waves. But it absorbs microwaves, infrared, ultraviolet. Why is this important? Well, the sun gives off the majority of its energy in the visible range. And so sun's radiation comes right through the atmosphere fairly well. The Earth being much cooler, it gives off most of its radiation in the infrared range. And the atmosphere absorbs some but not all infrared. So this is where we get the greenhouse idea. Radiation from the sun comes right through, hits the Earth absorbs it, heats up the Earth. The Earth gives off its own radiation, but that radiation goes up and some of it gets trapped in by the atmosphere. So if you have radiation comes in, but doesn't go out, then you have a net heating effect. You had more heat coming in than going out. Well, if you have a net heating effect, what happens to the temperatures? They go up. They go up, and as the temperature goes up, because radiation efficiency is proportional to temperature to the fourth power, you increase the temperature a little, the radiation given off by the Earth increases a lot. And so as the temperature increases for the Earth, the amount of radiation it's producing goes up a lot, which means the amount of radiation that gets out goes up, until you reach a balance for the temperature of the Earth that makes it so the radiation coming in from the sun balances the radiation leaving from the Earth. But the more you block, the higher the temperature of the Earth has to be to reach that balance. Does that make sense? Now, if we had no greenhouse effect, what would that mean for the temperature on Earth?
You get really hot and then really cold.
Well, the really hot, really cold is, it would get really cold and go from really cold to colder. If we had no greenhouse effect, we'd freeze. There'd be no life here. So the greenhouse effect is absolutely vital if we're going to have life on Earth. But the problem is that the greenhouse effect gets too big, then you're like Venus. Venus has what we say a runaway greenhouse effect. The greenhouse effect on Venus is so strong that the temperature on Venus is like 800 Kelvin everywhere. What would happen to life if we were on Venus? Yeah, we would be incinerated. Now, Venus has some other problems. It's also chemically hostile, so that would also be a problem. So too much greenhouse effect, no life. Too little greenhouse effect, no life. We need to have it just right. Now, how does all of this play into politics? Everything I've said has nothing whatsoever to do with politics. How does it have anything to do with politics? The what? Well, it's real. If it wasn't real, we would all be dead. The question is, how much is man responsible for changes in the greenhouse effect? Right? If man, we know that man, by doing things like domesticating cattle and eating those domesticated cattle, we're increasing greenhouse emissions by an enormous amount. Greenhouse emissions are gases that, when they get up into the atmosphere, are going to increase the absorption of infrared radiation. And if we increase that, we're going to raise the temperature. And so the question is our propensity to eat meat, or our propensity to have industrialized plants that are burning things and producing carbon dioxide and whatnot, are those contributing to the greenhouse effect, making the Earth warm up more than it would naturally? And if so, are we then causing the flooding of island nations? Is New Orleans, that's already below sea level, going to become even more below sea level? And so that's where it becomes a political thing. The science is not clear if man is responsible or not. Some people say, oh, science is clear that man is responsible. Other people say, oh, it's clear that man is not responsible. Well, if you have people that say it's clear both ways, I'm going to go with it's not yet clear. But we do know that that greenhouse effect is real. And whenever I talk about this, I use as my takeaway, we still always need to be responsible. Right? We live on this earth. We need to be responsible to this earth, to not pollute and so on. So whether you believe that man is responsible for greenhouse emissions or not, you still should be careful with what you do. Or not the greenhouse emissions, but the greenhouse effect. And, leave a planet for those behind us. So let me just move on from that because we only have 5 minutes left. Which kind of heat is involved in the greenhouse effect? Sorry, can't answer yet. Now you can answer. Okay, so Tyler, you already answered. Why don't you come up and see if you can make that thing work now? I'm praying a little here. Okay. We got pretty good. Most people said radiation. The greenhouse effect has to do with radiation because we have the sun's radiation that comes right through, the Earth's radiation that gets blocked. There's one person that said induction. I have not used that word today. And one person that said convection, which is at least a relevant topic. Okay, now we're going to talk about, I hope, heat engines. So Tyler is working on hopefully making a demonstration of the first heat engine. So he'll get it set up and then we'll leave it to run throughout the lecture and see if it actually works. Don't like the sounds of that? No. Heat engines are useful to us. The purpose of a heat engine is to convert thermal energy into mechanical energy. Now, one person on their potential test question from last class period had a statement of the second law that relates to this that I have not talked about yet, so they lost a point there on relevance. Now it would be appropriate. One statement of the second law of thermodynamics is that you cannot perfectly convert thermal energy into mechanical energy. Now you can convert mechanical energy into thermal energy real easily. Take your hands, put them together, go like this. What happens? They get warm. You converted the mechanical energy of the moving hands into the thermal energy of the hot hands. That's very simple. But going the other direction, you can't take your hands and make them cool and they move because you cooled them. You can do some, but not a lot. And so the heat engine that Tyler is putting together here is called a Hero engine. It's showing how we can convert some thermal energy into mechanical energy. So he has here, and this was what, Hero of Alexandria, who, yeah, just slide that under, who first made this, just a soda can that has some water in it. And he's going to heat up that water. What happens to the water when it heats up? You're going to get some boiling, some vapor coming off, and that higher pressure that's produced when it expands is going to come out, and he has flaps cut in the sides, so if all goes well, it should start rotating. That was the first heat engine ever developed. Mechanical energy, that rotation was mechanical energy. The thermal energy, of course, is from the burning flames. Now I have here, we are so low on time. I have a diagram showing a heat engine. A heat engine always has a hot region and a cool region. And you take heat from the hot region, and some of that heat is going to be converted into work, and some of it is going to be exhausted. You take an automobile engine. An automobile engine, the heat at high temperature is the burning gasoline. The heat at low temperature, have you ever felt the exhaust pipe of a car or a motorcycle? Usually it's by accident. No one? Wow. And I say, you guys live protected lives. My little sister, the one that's in this position, she put one leg on the tailpipe of the moped, a big burn. The next week, A different moped that had the heel pipe on the other side, put the other leg on. So she had burns on both legs. Because those things get hot. That is the exhausted heat at low temperature. For a heat engine, well, I am so out of time, but I need to at least show this. Here's the Otto cycle, Otto name for the, oh, excellent. Well, it's starting to work, but it's also, the gas coming out is a little problematic. Yeah, you can see it's working. The Otto cycle is the cycle used in a 4-stroke engine, and I guess I'll have to talk about the Otto cycle at the beginning of class on Monday. But our Hero engine is starting to work. Hooray for the Hero.